Good afternoon and welcome to our webinar on marketing mix modeling and optimization with Bayesian Networks and BayesiaLab. I'm delighted that you can join us today. Let me start off by introducing myself. My name is Stefan Conradi and I'm the managing partner of Bayesian USA, and I will be your host today. But beyond me, really the star of today's presentation is BayesiaLab. That's our software, our principal product that allows you to encode, learn, edit, perform inference, analyze, simulate, and optimize all with Bayesian Networks. So this is what you will see this afternoon in practice. So let me give you a quick overview of what to expect today. We will start off with an introductory example, kind of as motivation and background. We will talk about a fictional product, the generic 2000 new vehicle launch and a commercial for it. In this context, we'll see some of the difficulties of an establishing causal effect. You will see an example of Simpsons Paradox, and that introductory part should probably take around 20 minutes or so. After that, we will get into the marketing mix modeling workflow proper. We will take a data set and see how, with the things we learned earlier, can perhaps build a new causal model that would allow us to analyze effects and ultimately optimize. But what we will realize that for this data set, for this more complex domain, we will be in trouble. In fact, we will not be able to solve it. So here, a major new finding comes in the form of the disjunctive cause criterion. We will see how we can use that in conjunction with machine learning with BayesiaLab to build a model that ultimately allows us causal inference and optimization. That is the ultimate objective of this afternoon, and the second part should take approximately 40 minutes. So one thing I should point out is that everything that you will see today will be available in the form of slides, data, and a recording of the webinar. Now, given that today's program is very full, I will not have time to go into a lot of details regarding some topics, so I'd like to refer you to our book that is still available for free download on our website. So please take a look at that. Many of you, I think, will already have downloaded it. So let me get straight to our example. And for those of you who know me, you will not be surprised that this case study once again relates to the auto industry. But I think it's a practical example that everybody can relate to. So imagine you worked as a marketing manager for the generic car company, and you are in the process of launching a new model, namely the generic 2000. And to launch this product, let me make sure things move to the next slide. Here we go. To launch this product, the generic car company runs a commercial at the Super Bowl. That's when really the car makes its debut. And as you can imagine, such a commercial at the Super Bowl costs millions to produce and millions to air during the event. So given that you're the marketing manager, you obviously want to evaluate how effective this commercial was, and therefore you hire a market research agency to study that topic for you. More specifically, you conduct a survey of 1,000 car shoppers to understand the effect of the Super Bowl on not just purchasing behavior, but also shopping behavior. Specifically, survey respondents are asked about whether they've seen the ad. That's the variable for ad exposure. Then gender, what is your gender? Did you do a test drive of the vehicle? And then finally, did you purchase a generic model? So, and what we need to bear in mind is that all of that is observational data. So this is unfortunately not an experiment. Rather, we're asking after the fact whether people have seen the ad and then purchased the car. So you're obviously very eager to get the results back from the marketing or from the market research agency, and you immediately run a crosstab with Excel. Your boss, the VP of marketing, is waiting for the results as well. But unfortunately, the initial result that you get from that crosstab in Excel is a bit surprising. It appears, when you summarize all 1,000 responses, that those individuals who did not purchase or who did not see the ad purchased the generic brand at a 60% rate. For those who saw the ad, they purchased the vehicle at a 45% rate, a drop of 15%. So that is obviously very troubling, and that you perhaps don't want to share with your VP of marketing straight away. So what we do in marketing science, we slice and dice our data until we find something that we like. So now we're looking at the data, and we group the data by gender, male and female separately. And lo and behold, we see something interesting, and that is among the men who saw the ad, they had a higher purchase rate, and the same applied also to the women who saw the ad. So plus 5%, this really sounds a lot better, and this commercial may be worthwhile after all. But now, well, which one is it? You know, now we have two crosstabs, two tables that represent this very same underlying data. How is it possible that looking at it for male and female combined, we have what seems a negative effect, and if we look at them separately, the effect is positive? Well, what we have here is what is known as Simpsons Paradox, which means that an effect can appear in subgroups of the data, but it can disappear or even reverse when these groups are combined. So that is the problem here. So what do? In fact, it isn't over yet. In a way, we have a double Simpsons paradox, because if we continue to slice and dice our data, we see, and for instance, we group our data by test drive, yes and no, it looks like we have an overall negative effect, an even more negative effect than what we saw before. Now, if we finally group the data by gender and test drive, it seems like it's evening out. So now what? Now we have 4 crosstabs, and each one of these 4 suggests a kind of a different effect. So what is the true advertising effect that we have here? So I would like to ask you that question and run a quick poll that lets you assess whether the ad was positive, negative, or perhaps neutral. So I launch a quick ad and get your read. So this should momentarily pop up on your screen, and I will watch here as the results are coming in. So I'll just wait here for a few moments. We have a very good participation rate here. We almost have 70% of webinar attendees vote. All right, perhaps it's time to close the survey. Let me just close it here right now, and perhaps I can immediately share the results with you. Let me just see that I can hold on. No, that's not what I wanted to do. Let me showcase the results. Okay, here we are. 58% of you thought the ad was positive, almost 40% thought it was neutral, and 4% consider it as negative. So even though we have a majority, there are still some who are not convinced that this was a good ad. And so you might perhaps be tempted to think, well, let's use some statistics here. Let's use perhaps some data science to resolve this question. So, okay, we're back on PowerPoint. And of course, we all talk about big data these days. We are collecting lots of data from many different sources. So let's look at our data more closely and perhaps use some statistics here, or perhaps start with some regressions. And in fact, I'm now creating 4 regression equations that each correspond to the tables that we saw earlier. And now, instead of just looking at the crosstab, now we're looking at the coefficients of ad exposure, and they correspond to what we saw earlier. So now, well, perhaps you might be tempted to say, well, can we just take the best fitting of these? Is that perhaps a way to discover which one is the important one, the relevant one for our purposes? Well, no. What we need to realize is that what we have is really a generic type of equation, y equals f of x, and that can really is entirely ambiguous, because that equality sign can mean 2 things. It can refer to, given that we see y is a function of us seeing a value of x that was assigned by nature. That is observational inference or prediction, which is totally different from us performing causal inference, from us evaluating y as a function of actively doing x, where we assign a value x of our choosing that is given that I do. Now let me put these concepts into our map of analytic modeling that you've probably seen many times before. Now we have given that I see on the left side, that is association correlation in terms of model purpose, and then on the right side we have given that I do, which relates to causation. So that's the main distinction on this map, left and right, association versus causation. And we need to understand that our ad, our commercial, whether it was a good thing to do, is a causal question. Was it good to do this commercial? So, given what I've just said, so which one is it now? Because all of these, clearly by default, can be interpreted as given that I see. They can be used for observational inference, and we can evaluate them for their statistical qualities, but we cannot say anything causal. But we need causality, we need causal inference, because we want to know whether it was worthwhile to spend millions of dollars. So let's now look at our map again and see where we stand. So in a way, we sit in the upper left-hand corner. We have models that reflect association. We have predictive models that allow us to perform observational inference. But where we want to get to is a causal model that allows us to do causal inference. And so perhaps you may be tempted to say, hey, let's collect a little bit more data and perhaps use better statistical techniques. But the answer is absolutely no. No amount of additional data will help you answer these questions. Instead of 1,000 survey responses, we could ask 100,000 shoppers, and that will not help us. And that's why I often like to refer to the fallacy of data-driven decisions. Why am I making such a provocative statement? Well, here in this case, in many other questions, we need something totally different than data. What we need is a story, more specifically, a causal story that will ultimately help us to get from a predictive model to a causal model. So going back to our map here, the path we need to pursue is this one here. We need to introduce our theoretical understanding of the problem domain, our assumptions, to get to a causal model. Now, of course, whenever we use assumptions, that is dangerous because our assumptions might potentially be wrong. But that's what we require here. So now, this is where Bayesian networks are extremely practical because they cover this entire spectrum of our map of analytic modeling. On the one hand, we can build Bayesian networks, we can machine learn them from data. On the other hand, we can also formally introduce our own domain knowledge into a machine learned network or create a Bayesian network entirely by hand. So, and that's what we will be using. We will maneuver in this entire space as we progress. So, our question now is, what's the story here? We have gender, we have ad exposure, test drive, and purchase. Those are the variables for which we have collected data. Now, the question is, how are they causally related? And when I use this example in workshops where I'm in the same room with all participants, usually takes about 2 minutes, and we all arrive at a consensus as to what that structure should look like. Now, there's sometimes a little bit of a discussion about the arc that goes from gender to ad exposure, why it is that way. But once we talk about it, that perhaps men are more likely to watch the Super Bowl, then all of a sudden that makes perfect sense. Given that you're a male, you're more likely to watch the Super Bowl, you're more likely to see the ad. So, and then you could think about, well, there are perhaps certain preferences that men versus women have with regard to brand choice, and so on. So there's usually not much debate at all about the remaining arcs in this causal network, or in this, what I should say, this is not just a visual representation of our causal relationships. This is actually the qualitative part of a causal Bayesian network. We can now expand on that and take our data from our survey and now estimate the conditional probability tables that represent the quantitative part of our Bayesian network. So we can simply read that in, estimate these parameters, and with that we have a fully specified and estimated Bayesian network that now allows us to perform inference. Most importantly, it allows us to perform causal inference because we can simulate an intervention. We can simulate an intervention to estimate the causal effect that is of interest, the causal effect of ad exposure onto purchase. Now, there are a number of ways how we can practically do it. It all boils down to that we wish to manipulate ad exposure while holding gender constant, which I've indicated here with this duct tape. So as we manipulate ad exposure, we don't want the gender mix to change. Now, the way this works in BayesiaLab and with Bayesian networks in general, there are actually several ways to do that. Perhaps the best known approach is to perform graph surgery. This has been proposed by Judea Pearl as a method for inference. We remove the arc from gender to ad exposure while maintaining the distribution for the variable gender. And then we manipulate ad exposure, turn it off and on to see what results. Or alternatively, what we can do in BayesiaLab is we can use a method that is called likelihood matching on the variable gender that fixes those probabilities. And with that, we can then also simply try ad exposure on and off and get to our result. This is what this looks like in BayesiaLab. We don't have to surgically remove any arcs here. We can simply tell BayesiaLab our intervention variable is ad exposure. Once we've defined that, we can set our intervention. And in this case, the intervention is toggling back and forth between ad exposure off and on. We go back and forth. Here, I set ad exposure to 0, and we can look at what the purchase rate is at that level. So here we see at ad exposure 0, we have a 50% purchase rate. And then once we set ad exposure to 1, we see we have a 55% purchase rate. So this tells us that the true causal effect is plus 5%. So the majority of you were actually correct in their initial response to all those 4 tables. So the one table that conditions on gender and does not condition on anything else, that is the one that gives us the true causal effect. So you may say, couldn't we have done that without Bayesian networks? Yes, we could have. Perhaps intuitively, and many of you got it intuitively right. You might have immediately seen that, yeah, we just need to condition on gender, and by including gender in a regression, we would automatically condition on it, control for it. But even in this fairly simple example, at least well over a third of our participants today didn't get it right. So as we progress to more complicated examples, you can see that it gets very quickly quite confusing, and it may no longer be entirely clear what we need to condition on and what not. And in a Bayesian network, representing the causal structure, that makes that very clear, makes it very easy to identify what we need to do. So, as I said earlier, this is the conceptual part of the presentation, which now concludes. Now, I want to stick with the example of the generic car company, but now we go from the national level to the dealer level. So now we know that the Super Bowl commercial was good, so that was successful. But now we're going to the Acme Generic Auto Center, the largest dealer of the generic brand in the country, and we want to help this particular dealer to optimize its marketing mix or media mix. I will use marketing mix and media mix interchangeably here. So we want to help them correctly allocate their marketing resources between all the different channels that they have available. Now, we may think this is perhaps a relatively new problem for advertisers because only recently we had this extreme proliferation of media channels with social media and all these things. But as it turns out, this is a fairly old problem. And this quote, the following quote, "I know I waste half of my advertising dollars. I just wish I knew which half." This has been attributed to John Wanamaker, Henry Ford, and J.C. Penney. I'm not sure who actually said it, but I think this is exactly the same problem we face today, except we have a few more channels to consider. So let's now specifically look at the use case or the case study for the Acme Generic Auto Center. this is what they have. Luckily, they have recorded their sales, marketing, and media data for quite a long time. They started early, and for that reason, they have almost several decades of sales and media spend. More specifically, these particular variables: TV advertising, direct marketing, print advertising, internet advertising, incentives. That's a very important one. Co-op promotions. This is when you have the manufacturer and the dealer jointly pay for advertising. Basically, if you pay half, then we pay half, kind of deal. Importantly, they are also tracking competitive incentives. So they know what other dealers and other manufacturers, how they support individual transactions, and so on. So this is all what they've recorded. And so perhaps you'll now say, okay, let's do the same thing that we did with the Super Bowl ad and introduce our theoretical knowledge about this domain. Let's create a causal network for all these variables. Great idea, but I think it's getting difficult. Yes, we could certainly start, and there are some variables that are totally intuitive. We can say, it is print advertising that causes sales as opposed to sales causing print advertising. That's fairly straightforward. But what about web traffic and internet advertising? Because when you do internet advertising, you need somebody to, have traffic in the first place, so you can bid on showing an ad to that to the person who searches on Google, etc. So there it's not entirely straightforward whether what comes first, or if you think about incentives, because that is obviously kind of a cat and mouse game where one manufacturer offers incentives, then the other one raises them, and then the other one responds again. So we don't know what comes first. Or even if you think about this co-op advertising, like if the dealer or if the manufacturer says, we co-fund your advertising if you do it, well, what is the cause then? So some of the relationships are easy to identify. Others, especially the relationships between our marketing variables, those are difficult. And so we will very soon run into a kind of dead end. Additionally, one of the problems is that there are so many possible causal graphs. I mean, a lifetime would not be enough to evaluate all the potential relationships here. So we can't do that really practically. And this is still a fairly simple example. Obviously, there are many more marketing channels that would have to be considered. So what do we do now? So this path of providing a causal network from our theoretical knowledge, that won't work. So what do we do now? We need a different kind of theory. We need to do something revolutionary here because our traditional approach won't work. In fact, there is something that is revolutionary, and that is the discovery of the disjunctive cause criterion. It was discovered by Van der Wele and Spitzer, and what they're saying is we can identify confounders not by looking at a causal structure, because that sometimes is just unknowable. Instead, we have a different criterion, and that is the following. We propose that control be made for any pre-treatment covariate that is either a cause of treatment or of the outcome, or both. So it's a very simple criterion that allows us to select confounders, what we need to condition on, without having the full structure. So this is what we can very easily implement in BayesiaLab. we can tell BayesiaLab to what we believe the confounders are, and then perform direct effects analysis and thus get to the causal effect, the advertising effect. What is important to know, though, is that we must assume that there are no unobserved confounders. That is something we absolutely must be sure of. Unfortunately, that is a non-testable assumption. We simply have to justify that on theoretical grounds. Anyway, so let's now put this back into our slide here, into our map of analytic modeling. Now we have new theory, and the theory is no longer knowing the full causal structure. The causal knowledge comes in indirectly through the selection of confounders, for which we now have a very simple criterion. That's the idea, and that is really very, very practical, because the predictive model we can very easily generate through machine learning. We will see that in a moment how that works. We can just take the data, machine learn a predictive model, and then take this non-causal model, this non-causal predictive model, pick our confounders, and then use that for our causal inference. And that is really, I think, quite revolutionary. So here's the workflow that we're going to use. And momentarily, I will switch into BayesiaLab. We start off by importing historical sales and marketing data. And you will understand that the data I'm going to share with you is synthetic. Unfortunately, I cannot share with you any real data from our customers. For some reason, they are very particular about keeping their data confidential. But on the plus side, given that this data is synthetic, hopefully realistic though, that will be available for download, and so you can experiment with that very data set yourself. So on that basis, we will machine learn a predictive model with BayesiaLab. We will use the disjunctive cause criterion to establish what are confounders and non-confounders. Then we use the direct effects estimation to obtain response curves, introduce function nodes for cost, and then it gets interesting because we will then proceed to optimization. We will use a genetic target optimization algorithm, and then comes something that many of you have waited for, and that is dynamic Bayesian networks. I will show you how we can perform network temporalization and show you how we can basically take the existing contemporaneous model and turn that into a dynamic model, and how we can perform optimization with that as well. So at this point, I will leave, hold on, let me just make sure I do this correctly. I will leave PowerPoint and share BayesiaLab with you. Make sure that that works. You should now momentarily see the BayesiaLab screen. I think here we are. Okay. Now we can start by bringing in our original data set. And what I forgot to point out earlier, for these types of calculations, we really need quite a lot of data. So this, if you just have 2 years of weekly media data, that will not be enough to estimate a complex model of this kind. So we're really talking about thousands and thousands of observations, which luckily in a modern marketing environment is becoming easier, simply because we collect data at much higher frequencies than we've ever done before. Anyway, so here's my data set. I'm bringing it in. This is the first step of the data import wizard. We now see that BayesiaLab recognizes the seasonal variables, the calendar variables, as categorical. Here are the first 4 columns, and then all the remaining columns are numerical continuous. So I don't need to change anything here. Now, here we would set the missing values processing algorithm. It's not even worth discussing it at this moment because we have so few missing values, so we can just skip over that. But one thing we do need to do is look at the discretization, and I'll just pick out one variable. Let's see, the showroom traffic. That is continuous that we now need to discretize. If we had specific domain knowledge, I could now manually introduce bins, and perhaps some values are of a specific meaning, perhaps some relate to key performance indicators of an organization. I don't know that though, so I will use one of BayesiaLab's most universal discretization algorithms, the R-squared genetic optimization algorithm, discretization algorithm. So let me run that here. So now we found it for the variable showroom traffic, but we now need to also do it for the remaining variables. So I will select all continuous and apply the same algorithms for the same algorithm for all of them. So let me click finish. So just take a moment. Okay, here we are. Make this larger. Let me stretch out the nodes a bit and make sure that they nicely fill the screen. So here are now all the variables we have from our original problem domain. And I said our next step will be to machine learn a predictive model. We now simply need to find a statistical representation of this domain to capture the joint probability distribution, and then separately our causal knowledge comes in through selecting the confounders. So let's put that aside for the moment and simply learn our statistical model. Now, we certainly want to focus it on sales. That is very clearly our target variable. Later on, we want to optimize for that. And then we go into BayesiaLab's supervised learning menu. And here I will choose without further explanation the augmented naive Bayes learning algorithm. And we could certainly experiment with others as well and see whether we can improve upon the model. But for now, I'll just start with this simple and quick learning algorithm. Okay, so here's our first network. Let's perhaps arrange this in a slightly nicer way. For this, perhaps the radial layout is appropriate. Okay, so now we have all our variables, our entire network nicely arranged. I can perhaps stretch this a little bit more. Okay, yeah, this looks nice. What I keep mentioning whenever we talk about Bayesian network learning is that we should do a sanity check. Does what we have learned make any sense? So perhaps the first thing that we should check on, that we should review is, or the first question I usually get at this point is, why are all the arcs outbound? You know, aren't we trying to predict sales or ultimately go beyond that and see what causes sales? Yes, we are. But remember, I said we are only going to build a statistical model for now. And for a statistical model, for a predictive model, a structure like this with all outbound arcs is way more parsimonious than one with all inbound arcs. Theoretically, a structure with all inbound arcs would be possible, but just for the fun of it, I calculated how many observations we would need in order to estimate such a structure. if we had all the arcs inbound, the table, the conditional probability table that is associated with sales would have to contain billions of cells, or not would contain billions of cells that would have to be all filled or estimated with observations. So yeah, I calculated that in order to estimate such a network, we would require 450 million years of daily sales and marketing data. And obviously, even some very traditional brands don't have that much data. So, okay, so this is more parsimonious. This is a more practical representation. But let me continue on the topic of does this all make sense? Excuse me. And let me bring up our mapping function. Make this a little bit larger. And now it seems like I'm losing my voice again. Okay, so here I have now represented our, excuse me, our network in a slightly different way using our mapping function. And I'm going to assign now mutual information to the node size and Pearson correlation to the arc thickness. This gives us a sense of how important individual variables are with regard to sales, but important only in the informational, statistical, predictive sense, not in the causal sense. That we will look at later. And here I would argue that probably makes sense that web traffic perhaps is even a proxy for sales. The more people come to your website, perhaps that is indicative of sales. Or calendar variables. People go car shopping on the weekend and so on. So we can look at that, or we can also look at the sign of some of the relationships. And one that is worthy to point out is perhaps the link between sales and competitive incentives. This suggests as competitive incentives go up, our sales go down. That's plausible too. So we could now continue our sanity check and see whether all this makes sense. Perhaps one more thing, and that is that certainly many of our marketing variables are all related, and that they are related to the calendar. So everything is related to everything else, it seems. So, but now let's get closer to the question of causality. So now I'm going to look for our confounders. What here needs to be a confounder so that we can proceed to causal inference? Now, by default in BayesiaLab, all variables are confounders. So if I don't do anything, every single one would be considered a confounder. What I need to do is define the non-confounders. And let's think about what is what. So I would argue TV advertising, direct marketing, print advertising, internet advertising, incentives, they would meet the criterion of confounder. Are they a cause of the treatment? Are they a cause of the outcome? The outcome is sales. So yes, all of these would be causes of the outcome. Same thing applies to the calendar variables. Clearly, by virtue of being a Saturday, that is a cause for more sales because more people go car shopping on Saturdays. So the calendar variables would be confounders as well. Now, what about the ones sort of in the bottom right quadrant here? Competitive incentives, web traffic, showroom traffic, test drives, co-op promotions. And intuitively, you would say, yeah, they are, web traffic drives sales, showroom traffic drives sales. Sure, but they are not pre-treatment. One can argue that web traffic, showroom traffic, test drives are effects in themselves, they are being caused by other marketing activities. They are not pre-existing variables, like the weather or like the calendar. So I would argue they belong into the class of non-confounders. Same thing with incentives, because incentives are not just a fixed value, but they respond to what we're doing. As we raise incentives, they raise incentives. So that is not something, first of all, that we can control, but it's also not something that stays fixed. Similarly with co-op promotions. Co-op promotions don't start up by themselves. They start up if we and the manufacturer come together and say, we do this jointly. Okay, so with that, I would argue that these variables here, they should all belong into the class of non-confounders. So I've declared them as such, and to visualize this a little bit, or to distinguish this visually, I will just assign a distinct color to all our non-confounders. So all the non-confounders are red. Now, I said all the calendar variables, they should be confounders, but they are a special kind of non-confounders because we don't have them under our control. They rather are what they are. We cannot increase the number of Saturdays, even though we would probably want to. So therefore, I'm declaring these as not observable variables. That may be a bit misleading or counterintuitive. I'm simply declaring for direct effects analysis and later on for optimization, we should not take those into account. So with that, we are at the point where we can perform our initial analysis, our first causal analysis, and for that I'm going to use the direct effects function in BayesiaLab. Let me run this. This should just take a short moment. And here is our results, our plot of the results. Okay, how can we interpret this? The x-axis refers to the normalized value of each of our marketing variables. So they're all on the same axis, so we can compare them because one variable may be measured in dollars, another one in airtime, so they may have very different units. Here, they're all brought onto the same scale. And then on the y-axis, this is the number of sales in units. So let's go through those one by one. Here is our response curve for TV advertising. So it seems to be fairly steep initially as we start with the low levels of TV advertising. And then as we go up, it kind of flattens out a little bit. Let's go to the next one. Internet advertising. That seems to be an S-shaped curve, initially flat, then it increases, and then it flattens out again. Next one is incentives. That has a pretty steep incline initially, and actually then continues almost linearly. Now what's next? Direct marketing. This is kind of curious. It seems like beyond a certain point of direct marketing, of a direct marketing spend, it seems to become counterproductive. And perhaps if we get too many calls or too many pieces of junk mail from a company, perhaps that indeed has a negative effect on our willingness to purchase. And then finally, print advertising. That's also interesting. It looks like beyond a certain level of minimum spend, kind of the curve is pretty much flat. So it seems like we need to do some print advertising, but then the exact amount or spending more doesn't necessarily, help us a lot. Okay, So these are our causal response curves. These are the direct causal effects of our marketing variables on sales. Now, how can we use that for optimization? Well, if we had unlimited budgets, we would simply pick the top spots of every curve. Let's say here, direct marketing, 50.82, that's how much we should spend. And then for, TV advertising, we just go straight to the maximum amount and so on. So, but of course, we don't have unlimited budgets. So what we need to do is somehow introduce cost. That's what I'm going to do next. I will create a variable, a special type of variable, a special type of node, more specifically a function node that I will label cost. And this is a node that allows BayesiaLab to compute or to summarize the values of all variables that we are considering here. And of course, we only need to sum up the cost of those variables we have to pay for. We have to pay for TV, direct marketing, print advertising, but we don't have to pay for month or for competitive incentives. Some of these are either free or somebody else is paying for them. And you see this little warning triangle here. This means that we still have to define how exactly we need to sum up these variables. And this is now a very simple Excel-style formula that I'm going to use, where I'm simply adding up the mean values of all my marketing nodes. And just to keep things simple, I will assign a cost of $1 for each of them. Now, of course, it's unrealistic because TV may be measured in minutes of airtime and print in number of pages, who knows? And so I could now include very specific cost functions. I could include price table, discounts, buy two, get one free, whatever my media vendor is willing to give me. I can include that all in here and take that into account for optimization purposes. So let me accept that, or actually validate first, accept. And now we're almost ready for optimization, but I need to formally tell BayesiaLab that the node cost belongs to a certain type of class of nodes, a predefined class named resource. This means that BayesiaLab will now look at cost as our overall budget variable. Okay, switching into the validation mode, going into target optimization, and of the three possible optimization algorithms, I choose the genetic algorithm. Comes up with a pretty big set of options here, and we don't have nearly enough time to go through all of them. In some of our other tutorials, book chapters, we go into a bit of detail that explain why they are set the way they are set. Here, I just want to point out a few things. We want to optimize the mean value of the target node sales. We want to maximize it as opposed to perhaps minimizing it. We want to certainly take into account our resources, our budget, and I can specify the exact budget that I have here. Now, I think it's good practice to start with basically the same budget that we've already had. So here I'm just taking the default value, saying how much more could we sell if we simply reallocated the resources we have historically been spending. And then with that as a starting point, then we could proceed and say, well, what if we could increase that, etc. Then important here, oh, hold on, I forgot one thing because I only want to optimize these guys here. I don't want to optimize on competitive incentives because they are obviously not under our control. So let me start this again. Now we're only looking at those variables that we can manipulate ourselves in this domain. I can set individual constraints because perhaps on some variables I'm locked into a long-term contract. With others, I have more latitude. Here, just to illustrate how constraints work, I'm setting a plus minus 50% constraint on each of our marketing variables. So within that constraint, we want to optimize. Okay, and now with that, we can let it run. I set a stop criterion that will automatically stop whenever BayesiaLab cannot find a better solution. So I'll just let that run for a while. And with a genetic optimization algorithm, we need to bear in mind that in theory, or not just in theory, but unless we stop it, it will just keep going and searching. That's why a stop criterion is important. Or we can also manually stop it here and just say, okay, I want to see a result now, so let's pull the plug. So I think given that we've only about 5 minutes left, I will pull the plug and stop, and then see what the best scenario is that we've found so far. Here's my report window. Expand this a little bit. And now I'd like to draw your attention to the table here in the center, to the row that is labeled best solution. This now shows us what the best solution is that BayesiaLab has found so far. It suggests we should reduce the amount of incentives, slightly increase direct marketing, increase TV advertising, increase internet and print advertising too. So basically, it's reallocating budget from incentives and distributes it to the other channels. With that, and that's what we see from the bottom table, we would get an increase of 31 units of daily sales using exactly almost precisely the same amount of resources. So that's the currently best status. And then of course, at this point, usually somebody remembers, oh, we have this contract in place, or we can't do that. And then you would go back, set new constraints, and then rerun the optimization again. But here I want to focus on something else, because you might rightfully say, hold on, this is all just done on a contemporary basis. We've only looked at each day by itself, rather than taking into account that some of these measures or some of these activities have a lingering effect. My TV ad that I run today, or that I ran yesterday or a week ago, may still have an impact on the behavior of car shoppers. So there's a lag effect that we have not yet captured here. So of course we can do that. And now, unfortunately, we can no longer stick to the radial layout. Rather, I will change the alignment and create a vertical distribution of my variables. So they're now aligned this way. And next, I will use BayesiaLab's temporalization function. This creates a temporal clone of all these variables, so we can estimate the lags. To keep things simple and to keep the screen manageable and not overwhelm you with too many nodes, I will simply introduce a single lag. You now see that we have here a second row of nodes, and they are now labeled as T-1. let me just pull out here sales. Sales is still connected to all my nodes in time slice t. And momentarily, I will also link sales to all the variables, all the nodes in time slice t minus 1. But there are some nodes that I should probably remove in t minus 1, and these are the calendar related variables, because they may not make much sense, because if today is Friday, then inevitably yesterday is Thursday. So knowing that yesterday was Thursday isn't really giving us any extra information. So those I have removed, and then furthermore, I'm also removing sales for t minus 1, because that itself would not be a driver. Okay, now I'm connecting sales to t minus 1. I'm basically, here we go. I'm basically taking a little shortcut here, and or I'm basically simulating the augmented naive Bayes algorithm. I'm just approximating that, or I'm kind of I'm doing that manually instead of doing that automatically. I am declaring all my nodes as fixed, and I am now doing the augmented part of the learning with a taboo learning. Okay, so this is what I wanted to show you, where something got hung up, but for some reason that always happens whenever I have GoToMeeting running in multiple screens in BayesiaLab. Perhaps I need to get a faster computer. So this is what I wanted to show you. I wanted to demonstrate how we can perform exactly the same target direct effect analysis also with a temporal network, here with one lagged time slice, but we could certainly extend it to 2 or 3 or whatever you hypothesize being the relevant number of lags to include. But then comes the interesting part as we go forward, and we could certainly then also optimize on that structure again. Then we're taking into account that whatever marketing activity we do today, that will have a lingering effect, and that kind of still plays out over time. So the way we capture that here is as we simulate values for our contemporaneous values, we link them to the lagged variables via constraints. Here you, actually I should show that the appropriate slide to you. Here you see these little green dots, these little green nodes. They are our constraint nodes that link the marketing variables of t and t minus 1. Then we can run exactly the same optimization again. Now, that will take a bit longer because the computational effort becomes greater, but then we get a similar result, hopefully a similar result. One thing I would tell you probably from experience, whenever I compare results of optimizations that include lags and compare them to just contemporaneous models, often I'm surprised how little comes in via the lags. The strongest effects remain in the contemporaneous time slice. But that's perhaps just my experience. In other domains that may be completely different, and I would encourage you to experiment with that. So in conclusion, our time is up. I would just want to quickly mention that our webinar series continues next Friday. We will finally leave the automotive examples and go to something totally different. We will analyze the capital flow of exchange traded funds. That will be an interesting example of unsupervised learning with BayesiaLab on April 20th. 2 weeks from today, we will look at the GIS mapping functions of BayesiaLab. That is also a long-awaited feature and should open up entirely new application domains for BayesiaLab users. Now, I would encourage you to consider our course program. It's on our website. Please join us on our BayesiaLab community, where interesting discussions happen on everything related to BayesiaLab. So please join this community. And of course, if you found this interesting, download a trial of BayesiaLab. Everything you saw today, you should be able to do with the unrestricted evaluation version. Here is the link via which you can apply. And then, of course, I want to promote our course program. Perhaps you can still make it to the course in Sydney, Australia. That starts next week. We have several spots available, so if you're interested, just reach out to us and let us know. Then after Sydney, our course program continues in the US. Then later in summer, we'll be in the UK and India and so on. And one final event I would like to point out, and that is our annual BayesiaLab conference that runs from November 1st to the 2nd with courses before and after, introductory course before and introductory course after. I hope you can join us. We expect some great presentations from many different BayesiaLab users around the world. Well, with that, I really appreciate that you took the time to join me this afternoon. I would love to continue the conversation. Here are our and my contact details. Please do feel free to reach out. And with that, thank you again and have a fantastic weekend.